Yo, it's your boy Jay Good with another episode of MathLab. Today I'm just going to do a bunch of random problems from college algebra. I know the semester's starting. You know, a lot of people are going to be taking, a lot of freshmen are going to be taking college algebra, and even some sophomores or juniors, in which case that's okay. But this might be some of the things that you see along the semester. So let's dive into it. Alright, so we're going to talk about the composition of functions. Alright, this is a popular test question as well. And it's not hard, but of course if you miss class or you're sick or whatever the case may be, if you missed that lesson, this is a good example for you to get a good understanding how to conquer any composition of functions problem. So we always start with the innermost parentheses or the very tail of the composition problem, whatever it wants you to find, right? Typically they'll give you two functions, a function of f of x, a function of g of x, in which f of x is x squared and g of x is 3x minus 4, right? And we're just going to start at the innermost parentheses by plugging our 2 into x the first time. So without all of this, right, we just have f of 2. So we're going to do that first. So if we plug in 2 for x, we get, I'm going to put it over here, f of 2 equals 2 squared, which equals 4, right? So f of 2 equals 2 squared is 4, right? Plugging the 2 into the f function, okay? That's this part, right? That's our f of 2. So now we want to find f of 2. So we want to go out 1, okay? So we found that this is a number. This whole thing here is 4 we just found, right? So now we're going to plug that 4 into another function of x, all right, of the f of x, right? So we have f of 2, right, to equal 4 squared. Which equals 16, right? So we have 16 to equal f of 2. So we have all of this part of the composition to equal 16. That easy, right? It's not hard. So now we plug in 16 into the g function, our last part of our composition. And you can see how, you know, a question could be g of f forever and ever, because this is going to, each time you do this step, it's going to give you another number, and then you just keep plugging it in. That's all our composition is. So to finish it off, we plug in 16 in the g of x. And I'll go through this fairly quickly. G of f of 2, right, equals 3 times 16 minus 4. And your boy Jay Goo gonna go ahead and do that math for you. It's gonna be 44. So if you did you paused the video and actually worked it out beforehand, you should get 44 after this composition. So that is a composition of functions problem. It's not that hard, and it's a good refresher going back into school. Okay, so in this example, we're going to be doing the domain of functions. And this is another popular question, especially in the college algebra section, because it really wants you to understand geographically what a domain is, in range for that matter. A domain is just what numbers we can plug into this function as x, okay? So this is a function of x, right? And we want to know what all numbers are valid to make this a real number, or a number that exists, okay? So a domain is like where this number stays, where this number lives, okay, where this number exists. Is it this universe? Is it another? That's what we mean by find the domain. And so we just have to find all the restrictions that we have on the x in order to find the domain of x. Okay, so it's really not hard if you understand what domain is. Okay? So if we look at our answer choices, we have x is greater than -3. All real numbers, which means any number, negative or positive. We have x is greater than 0. We have x is greater than or equal to -3. And then we have x is greater than or equal to -3 and x is greater than 0. as our answer choices. Okay? So, first we have to ask ourselves, what are all our restrictions on x? Okay? And so, for one, anytime you have a fraction and you're given a domain question, the number one thing you have to, or the number one thing that should pop into your head is the bottom can't be 0. Because if the bottom is 0, if you have a fraction and the bottom is 0, that means it does not exist, literally. So the number does not exist if we have a fraction with the bottom being 0. That number does not exist. It's not a real number. Okay, so therefore it's a restriction on x. That means we have to denote that when defining our domain. Okay? So that's one restriction, is the bottom can't be 0, right? So that means we're going to have, as part of our answer, x is greater than 0. Okay? But let's see if we have any more restrictions on x. Okay? We can't have, alright, so we have a radical or a square root in the numerator. Okay? And another popular thing in college algebra is complex numbers. So when you have a radical, you can't take the square root of a negative number. Okay, so let's write that down. Cannot take square root of a negative number. You cannot do it. These are the two key things you must know when it comes to defining domain, and you'll be fine for any question regarding domain. Okay? So the 0 is at the denominator, which means the bottom of the fraction. It does not exist. And we denote that by saying that x has to be greater than 0. Okay? Which is here. We have that part of our answer. Next, we know that we cannot take the square root of a negative number. So whatever number will make this negative, then x has to be greater than that number. Okay? So if this is a negative 3, we have 2 times negative 3, which is negative 6, plus 6 is 0. Now, 0 over negative 3, this is equal to 0, which is a number, which is valid. This is not the same as this. Okay? So 0 over negative 3 is 0, which is a valid number. Okay? But anything less than negative 3, let's try negative 4. So 2 times negative 4 is negative 8, plus 6 is negative 2. We can't take the square root of a negative 2. Right? That's if we're using x as equal to negative 4. It doesn't work. So we see that the last number that we can use, which gets us a 0 in the numerator, is negative 3, right? In which we can take the square root of a 0 because it's just 0. So we have to also include in our answer that x is greater than or equal to negative 3. So all the numbers greater than negative 3 will produce a positive number. So they'll be valid for the numerator, right? Starting with negative 3. If you go past negative 3, negative 4 and beyond, this numerator will be negative and you can't take a square root of a negative number. So when we define our range, given what I told you, right, when we define our range, we define it as the set, right, of x's where x is greater than 0, right? We don't want the bottom to be 0, right? So that's part of our restriction. And x is greater than or equal to negative 3, because our top has to be a positive number, right? And that is our domain of this function. Okay, for our last example, we're going to do another factoring problem. Okay, it's a step up from the previous factoring problems that we did, where we're only focusing on x squared. But now we're going to take it up to x cubed. Now I did mention, but I don't know how well it stuck, that our question is asking us to find roots, right? Which is what factoring is, and we've done it. But in our question, we have 3 roots, okay? So that should send off a sign, all right? So if you have 3 roots, that means that your polynomial goes up to the cubed function. So when we were factoring questions like this that only went up to the x squared term, all right? In which case it would have 2 roots. But since we're looking for the solution that has 3 roots, right? We know that whatever function we're looking for has to have a cubed in it, all right? So off top, we can eliminate anything that doesn't have an x cubed in it. So therefore, this answer, without even looking, is incorrect. Just knowing that we're supposed to have 3 or x cubed in our problem, because we have 3 roots, which means it hits the x-axis at 3 points, so it has to be an x cubed function. So this one doesn't even have an x squared. That only has 1 root. None? Of course not. So we're really only dealing with 2 answer choices at this point, right? So, factoring a polynomial with 4 terms that goes up to x cubed, it's just a little bit different, but not much harder, okay? So all we do is we separate the x cubed and the x squared term, and then the last 2 terms, which is x and then the constant. And then we factor. So, starting with A, we have x cubed minus 5x squared. We're going to factor that. We're going to put this big line here, and then we're going to factor negative 4x plus 20. Okay, so factoring this side, which we should know how to do, right? Our greatest common term, remember, is x squared. So we're going to take our x squared out, and we still have in the inside x minus 5. Right? On our right side, 4 looks like the greatest common factor, so we're going to pull it out. Or you can pull out a negative 4, it doesn't matter, right? Whichever, let's pull out a negative 4, how about that? So we'll put out a negative 4, and on the inside, all we're going to have is x minus 5. Okay, so when you're factoring this way and the term goes up to x cubed, what I do is I break it up, right, into the first 2 terms, which is x cubed minus 5x squared, and the next 2, which is 4x plus 20, okay? And when you factor, whatever you have in common, it'll just be 1. So since we have 2 x minus 5s, then we'll just have 1 x minus 5, right? Because if we can take it from this side and we can take it from this side, then we can take it from the whole thing. So it's only one time really that we're doing it. You get what I'm saying? So now we have over here, and then you just take whatever's left over as your other part of your factor, like this. So it'll be x squared minus 4, because that's what we have left over, right? This is, we can't factor out an x squared from this side, and we can't factor out a minus 4 from this side, so we put them together, right? And then we have the x minus 5 that we factored from both sides. So that's going to be 2 of our roots, and then the x minus 5 is going to be a root. So we have x minus 4, and then we have x minus 5. Okay, and remember, to find our roots, all we're going to do is solve for x. So if we solve for x on x squared minus 4, we'll get x squared equals 4 by moving the 4 over on the other side of the equal sign, because right now we're setting both of these to 0 to solve for x, if you remember from the last factoring video. So I'm not going to write that down. If you don't remember, go check out the other factoring video. Okay, so here we're at x squared equals 4. Alright, now we have to take the square root, which is kind of what we talked about in our domain example. Alright, so we're taking the square root of x. So anytime you take a square root of a number, it's going to be plus or minus that number, which is why we produce 2 different roots, right? So this is going to be plus or minus 2. But in the situation of complex numbers, we just use I to determine, plus or minus. which is here, 2i and negative 2i. And the I is just imaginary number, right? Because you can't take a square root of a negative number. So when we take the square root of x squared, we don't know what type of number it is. We get plus or minus 2, right? So that's 2 roots. And then, of course, when we solve for our 5, we're just going to get x equals positive 5. Because we add 5 to this side, and then there's an equal sign here, equal to 0, and we add 5 to that other side, which will just give us x equals 5. So this is our 3 roots, right? Plus or minus 2, negative 2 plus 2, and our 5. So A is our correct answer. And that's how you factor a polynomial with a degree of 3. And it's the same thing as if it keeps going up. You just keep breaking it down. Okay? And that's it.